In our first lesson, we're going to take a look at how the structure of the atom changed in terms of atomic theory from the beginning of the atomic model until about the early 1900s. We're going to start first with Aristotle. Aristotle gave us the first idea that elements actually existed. The four elements that Aristotle believed to be in existence were air, water, fire, and earth. And pretty much anything that was a combination of these elements then was considered to be matter. The problem with this hypothesis, though, was the fact that it wasn't testable. It was impossible to test that certain materials were different proportions of water and air and fire. Democritus was another Greek philosopher, and Democritus believed that you could take an object like a stone, break it into the smallest pieces of stone that still have the properties of stone, and he gave that a name. He gave that name atomos, which was a Greek word which meant indivisible. So, according to Democritus, something could be broken into the smallest pieces of that substance, and that's where we got our name for the smallest particle of something, which was called an atom. So we had Aristotle, who gave us the idea of elements existing. We have Democritus, who gave us the idea of atoms, and other scientists later in England and France built on those two ideas. John Dalton was really the first scientist. He was an English scientist to take a closer look at atomic theory. He worked in the early 1800s, and he summarized his atomic theory as 5 postulates. He really was a meteorologist, so some of the experiments he actually did, but for a lot of his atomic theory, he actually took ideas from other scientists that had done work before him, specifically Lavoisier and Proust, and he had also read about the ideas that the two other Greek philosophers had come up with. The first postulate of Dalton's is fairly simple. All matter is composed of tiny submicroscopic particles called atoms. So oftentimes we call John Dalton's first postulate, or we give the name to the model, the billiard ball model, because we say that his idea of an atom was a spherical ball that could not be cut into smaller pieces. Postulate number 2 was that atoms are the smallest component of matter, and they're all indivisible. So imagine little golf balls, and that's the smallest piece that we can break something down into. Now, this postulate was actually disproven later by the existence of protons and neutrons and electrons, but for the time being, we assumed that atoms were the smallest piece of matter. The third postulate simply says that if you have atoms of whatever element A is, if it's atoms of helium, all atoms of helium are identical to another. This is another postulate that was later disproven by the existence of something called isotopes, which are atoms of the same element that have different numbers of neutrons, but for the time being, we assumed that all atoms are the same and identical to each other. Postulate number 4 is that when we form compounds, they are simply ratios of the original atoms that make up the elements that are bonded together to make those compounds. So in the case of water, it would be 1 part oxygen for every 2 parts hydrogen. And number 5, chemical reactions involve the rearrangement of atoms. This was also a restatement of the law of conservation of mass, that mass cannot be created or destroyed at the end of normal chemical reactions. And for the most part, postulates 4 and 5 stood the test of time as we move through our atomic model. The next scientist that really spent some time looking at the structure of the atom was J.J. Thomson. J.J. Thomson worked with cathode ray tubes. Now, cathode ray tubes were vacuum-sealed tubes that had voltages applied, and it caused a beam to move through the vacuum-sealed tube. Nobody at that time really knew what the beam was made out of, but there were some observations that J.J. Thomson made regarding this cathode ray. The first is it kind of bent a little bit when you applied a positive and a negative field. A magnet also caused this field to bend, and more importantly, this beam seemed to bend away from the negative side of the electrically charged plate, and it was attracted towards the positively charged plate in that setup. He also did some math, and he was able to determine the exact angle at which it was bending to calculate the mass of whatever it was made up of. Some important observations of J.J. Thomson's experiment: the beam traveled from the negative to the positive electrode. Observation number 2, the beam of particles was also attracted towards the positively charged plate later in the apparatus. And his third observation, he used a little bit of math based on the way that it was bending in the presence of the magnets, the magnetic field, and it was determined that the beam had particles that were 1/2000th the mass of a hydrogen atom. That means that whatever was inside of this cathode ray was certainly smaller than an atom. And this is the first time that anybody had discovered a particle that was smaller than a hydrogen atom. Thomson discovered the electron because electrons are negative, they were attracted towards the positive plate, and they are certainly smaller than the atom. When we take a look at Thomson's model, we call it the plum pudding model. The plum pudding model simply says that electrons were sprinkled in some sort of jelly, or I kind of think of it like cookie dough, where you have the batter and you have the chocolate chips, where the electrons would be the chocolate chips. And then those electrons, he thought, were stuck inside some sort of positively charged goo, and that kind of held the atom together. We now know that this model is not correct, but this was the model that we used up until the work of Ernest Rutherford. Ernest Rutherford and his research team were actually experimenting on radioactivity. So they had discovered that radioactivity was made up of 3 types: gamma rays, beta rays, but more importantly, they were working with alpha particles. Alpha particles are positively charged particles that originate from radioactive atoms. They're composed of 2 protons and 2 neutrons, and they basically get shot out from the inside of the nucleus. The most important thing is they're positively charged. Rutherford's graduate students expected all of those alpha particles to move all the way through their target atom, which was gold. They picked gold as the target atom because atoms of gold are very large. The initial prediction was, hey, these are like cannonballs of positive charge, and therefore all of these alpha particles should shoot through very easily that very loosely held together plum pudding from the Thomson model. But what they didn't expect was when the alpha particles began to hit the gold foil, they deflected at very strange angles. And this was very confusing to the scientists that were studying the experiment, because they expected all of them to go through. Most of them actually did go through without hitting anything, but some of those alpha particles were hitting something solid. And so this was the point during which Rutherford and his graduate students discovered that those alpha particles were bouncing off of something that also had a very strong positive charge. They discovered the nucleus. The nucleus is in the center of the atom. So those alpha particles had a positive charge. They were hitting the nucleus and being repelled by the nucleus because 2 positive things repel each other. And a lot of the alpha particles were actually going straight through, which meant that the atom is actually mostly empty space because those alpha particles were able to make their way through. So, at the end of the Rutherford experiment, we have 3 very important observations about Rutherford's atomic model. First of all, he and his team said that there is a massive positively charged thing in the center of the atom, and we call that the nucleus. It has most of the mass of the atom, and it's very positively charged. Number 2, electrons exist in the outside part of the atom. They are not in the center of the atom. Observation number 3, those tiny electrons that are in that empty space are actually in mostly empty space. Because most of the alpha particles were able to move their way through the gold foil, Rutherford and his team assumed that the atom was mostly empty space. Building on top of this, we're going to talk a little bit about protons, neutrons, and electrons in our next lesson.